Welcome to this video. In this talk, I will present a joint work with Andrew Shi from Cornell University and Paul Gay from University of Po. So the title is Forget SGD, Learn Sparse CNN with MCMC. So here is the outlines of this talk. I will just start with an introduction about convex optimization, gradient descent, and mirror descent. Then I will present the main mathematical results dealing with back Bayesian theory and online learning applied to deep learning. And then I will show you some experiment showing that MCMC sampling could be a good alternative to stochastic gradient descent in learning sparse deep nets. So just to have a gentle start, we start with convexity and gradient. So if you consider a convex function and you want to minimize this convex function over a convex body, then you can first show that if the function is differentiable, so you have this definition for the convexity, and then clearly you have that if y is the argument of the function, then the gradient, the negative gradient, is positively correlated with the direction y minus x. So this is a really good news, and it just motivates the use of gradient descent in convex optimization. So with this kind of things, you can show easily that the error rate of the gradient descent, the discrete gradient descent, defined as the following update here: x theta plus 1 is xt minus eta grad f at xt, satisfies the following theorem. So you control the error by a range term and a variance term. So the proof is very simple, and just use the standard equality dealing with the control of the drop at time t, which is here Euclidean drop. And then you can show just with convexity and telescoping term, taking the sum of this equality here, that your range is of this type. So it depends on the distance to the initialization, and your variance is just the L2 norm of the gradient at each f of xt. So this is very classical results in optimization theory. Interestingly, the gradient descent could be written as the minimization of these two terms. So here you have the scalar product between x and the gradient, and you have a kind of penalty which is implicit in the gradient descent, because when you discretize your space and your problem, you have to choose learning rate eta, and then in a sense you penalize by just the Euclidean norm to xt. Okay, if you differentiate this function, of course you find the update of the gradient descent. And what is important here is that with this penalty, you are completely Euclidean. You're in a Euclidean setting, and you have no localization. So you don't take into account what happens at xt, if there is some special geometry on the space, or if you have some information about the position xt in order to choose xt plus 1. You cannot do that with gradient descent and this kind of penalty. So to be more efficient, mirror descent is a generalization of this gradient descent, just to replace the Euclidean penalty by a Bregman divergence. So the Bregman divergence between x and xt is just the difference between, for some potential, convex potential phi, the evaluation of phi at x, and the linear approximation of phi at xt, with the gradient of phi at xt like that. Okay, so of course, if phi is convex, this term is positive. And what is very important with this gradient descent, mirror descent, is that actually by mean value theorem, you can show that the Bregman divergence is also an L2 norm, but with respect to the Hessian of the convex potential phi. So it's a quadratic form dealing with another geometry, non-Euclidean geometry, that localize the penalty at some point omega t, which is between x and xt. Of course, you can show easily that putting as potential the L2 norm like that, you have a gradient which is exactly x, and then an Hessian which is diagonal identity. So, of course, you don't do nothing here, it's just Euclidean distance, okay? And today, we are interested in putting a potential as a negative entropy. So, in this case, we will have interesting results in terms of sparsity, and we deal with optimization over the simplex. So we consider distribution as point in our simplex. Okay, so the main philosophy in this talk is to, in order to get good results, is to forget gradient descent and move faster when you are not sparse with this kind of potential as negative entropy. Okay, so now I will present the mathematical context and the main result of this talk. So we are in the framework of deep learning optimization and in the framework of supervised learning with convolutional neural network. So we consider a set of pairs xt, yt, classical supervised framework, where data rise time after time. It could be images, for instance, but also time series, etc. And we consider a set of decisions which is governed by a parameter, generally, which is weights of the network, which can be described like that. So it's a stack of linear operation written here with this matrix multiplication, and nonlinear activation written with this sigma here. Okay, so the neural network is a cascade of this operator, and then we have a loss function which is task dependent, for instance a cross entropy in classification, and our optimization problem at time t is to minimize the expected loss with respect to some distribution rho. Okay, so what we want to state in the theoretical result here is exactly as before when we compare the value of the function at xt and the value at the optimal x star. We want to control the expected loss at distribution pi t for any t in comparison with the infimum over this term. So this is the optimal that we want to reach, and this optimal weight is a trade-off between fitting the data and some penalty term, which deals with the complexity of the network. And in this talk, this penalty will be an L1 or L0 norm. Okay, so the algorithm allows to get this kind of result is called exponential weighted averages, or Gibbs sampler. So we have some hyperparameters, that is a prior pi in the set of positive measure with mass 1, a temperature parameter lambda, and you start with observing the first x1, and then you draw the first prediction according to the prior. And then for any t, you observe yt, and then you compute the next distribution, p t plus 1, which is a solution of the following minimization problem. So trade-off between the loss and the Bregman divergence at phi, which is in our case actually the Kullback-Leibler divergence, because phi is a negative entropy, and then actually pi t plus 1 as a closed form, and it is exactly just the L1 normalization of the exponential. So a Gibbs measure with the temperature parameter lambda. Okay, so now we can state the following sparsity regret bound. So consider your prior, which is a mixture of prior at each layer, and this prior is sparsity induced. So it means that it has EV tails. So like this, it's a power tail behavior, so a power law with exponent 4. And then with this prior, we can state this kind of result with a penalty which is proportional to the L0 norm of W. So if you choose lambda as 1 over square root of t times the L0 norm, you get the interesting rate square root of t times the sparsity index, so the number of non-zero coefficient of your optimal solution. Okay, so now we can try to sample from this posterior distribution, Gibbs measure. But actually it's a difficult thing. It's very difficult because we want to sample at each time t from this distribution, okay? But the problem is that the dimension of this distribution is huge. The dimension is exactly the number of parameters of your neural network. So for instance, in an easy one-layer convolutional neural network, it has 60,000 parameters, but for instance for VGG or AlexNet it has millions of parameters. Okay, so we expect some MCMC algorithm to tackle this challenge. Okay, so what I would like to show you is that a really simple greedy MCMC algorithm have kind of good result. So here is the algorithm. So you pick the first weight as the prior, so an EVTL prior, like a power law. You have a parameter lambda, and then for each mini batch m, you start with generating a Markov chain indexed by k. Okay, so to do that, you pick at random one layer in your neural network, and then you change some weight in this layer. So this is here the proposal distribution P, which depends on the previous value of the Markov chain, and just move some weights in this weight k, and then accept the move with some probability. This probability is classical. It comes from a Metropolis Hastings algorithm and ensure that you converge to the good Gibbs posterior. Okay, so in this ratio, acceptance ratio, you compare the likelihood in a sense of W tilde with respect to W k. Okay, so now we have made some experiments over the Cypher 10 dataset, and what we study is the resistance to pruning until 90% of the parameters of the network after training. So this first experiment shows the behavior of classical stochastic gradient descent. So we have 50,000 data for the training procedure. We have batch size of 256, and then you have around 200 iterations by epoch. It's important to compare to MCMC after that. So in this case, with a very simple CNN of just one convolutional layer and one fully connected layer, it has around 60,000 parameters. We consider no acceleration, no momentum, etc. And the accuracy over the test set behaves like that, epoch by epoch. Okay, so what you can see is a performance around 62-63% of accuracy in the test set at 300 epochs. And then here you have the degradation of the pruning version of the layer. So here you have CNN with just 10% of 20 or 20% of coefficients, and here you have 80% or all the parameters. Okay, so the degradation is high. I mean, it's not very robust to pruning. Here is the MCMC comparison. So if you run the previous algorithm, so this simple Metropolis Hastings algorithm with 200 MCMC iteration by epoch, and you consider the full batch size, okay, so no mini batch, so you just have 200 iteration by epoch. Here is the result. It goes like this. So what happens? We have comparable results. So we could have 50 until 58% of accuracy if we run more epochs, and the degradation, the robustness to pruning is better than a stochastic gradient descent if we compare these two plots. Okay? So we explain this very easily if we look at the distribution of the weight. So if we look at the density plot of the weight, for instance, the first layer, the convolution layer of the gradient descent optimization, you have here the distribution of the weights after one epoch, and then in pink after 300 epochs. So we see a distribution like uniform for the blue one and like a Gaussian with with a good variance, big variance after 300 epochs. And if we look at the MCMC distribution of the weight, the performance are a bit worse, but the distribution is really different. And if we zoom a bit, we can see the variation from epoch 1 to epoch 300. Okay, and so we see that there are some proportion of weight which are bigger than here stochastic gradient descent, but many parameters are around 0 for this distribution. So it's a kind of sparse distribution. If we compare SGD with MCMC, we can see the blue one, MCMC, which is sparser than the distribution of stochastic gradient descent. Thank you very much. Bye bye.